Hi everyone. So I'm going to be changing course a little bit, and I want to kind of step back and look at what we've done so far and think about it before we proceed. So the material that I'm going to be doing now is for the most part not in the text. I'm going to be posting a handout on Canvas pretty soon. Okay, so look, so far we've been concerned with good ways to reason and how to prove things. And we have developed a rigorous definition for validity and all the other semantic properties that we've been concerned with. And we've developed ways to prove that arguments are valid or invalid in arguments that are expressed in the formal language SL, the language of sentential logic. And we've got ways to prove that sentences in that formal language are logically true or false. We're calling them truth functionally true, truth functionally false, and that sets of sentences in SL are consistent or inconsistent. Okay, so we've talked about validity. We've developed this tree method for proving that arguments are valid or invalid. We have rigorous ways to prove that sentences expressed in SL are truth functionally true, false, etc. We have a way of testing and proving that sets of sentences are truth functionally consistent, and so on. Okay, so what we're going to do now is we're going to take what I'm going to call a metatheoretical interlude. And what we're going to do is we're going to prove that our ways of proving things work. So at the start of the semester, so this is something we've been taking for granted, right? We've been taking for granted that the tree method, we use it to prove that an argument is valid or an argument is invalid, or a set of sentences is truth functionally consistent or inconsistent, and so on. But what we're going to do in this metatheoretical interlude is we're going to prove something about our method. We're going to prove that our method that we're using to prove things actually works. It does what we're using it to do. And of course, we've been assuming this. We've been taking this for granted all along. So as I said at the start of the term, people have been concerned with determining what constitutes good reasoning and with developing ways of proving things for well over 2,000 years, starting with Aristotle, who was sort of the first person to do this in a more formal way. And our language SL provides a way of translating certain kind of sentences and arguments. So we've developed this argument SL, which is our formal language, that we're using to capture the formal structure, the logical structure, or a certain aspect of the logical structure of sentences and arguments, and so on. And validity is the rigorous standard that we've come up with. So truth functional validity is the rigorous standard that we've come up with against which we measure arguments. And our tree method is the method that we've developed to determine which arguments, tree method. The tree method is the method we're using to determine which arguments meet that standard. So we're using the tree method is used to determine which arguments meet that standard. So we've actually done a fair amount so far. We've developed this formal language that captures the logical structure of sentences. We've developed this formal, rigorous standard against which we measure arguments. And we've developed this technique, the tree method, that we can use to determine which arguments meet the standard and which ones don't meet the standard. Okay, so during this metatheoretical interlude, we're going to do two things. The first thing that we're going to do is we're going to show that the language SL is adequate for the purposes we're using it. And this is actually in Chapter 6. It's in one section of Chapter 6. We'll talk about that in a bit. The rest of Chapter 6, you don't have to read it all. The second thing we're going to do is, and we're also skipping Chapter 5. Chapter 5 presents another method for determining validity and so on, called natural deduction. And we're not going to be doing that, or derivations. I'm not sure what the book calls it exactly, but it's a different system for determining whether arguments are truth functionally valid. And so Chapter 6 in the text kind of does what we're going to do for Chapter 4. So you don't have to worry about Chapter 6 for the most part. I'll tell you which section we're going to be talking about. Okay, the second thing that we're going to be doing after we talk about the adequacy of the language SL is we're going to show that the tree method is adequate for its purposes. That the tree method is adequate for testing the validity of arguments. That are expressed in SL. That is, we're going to show that if an argument is valid, is truth functionally valid, then the method's going to give us the answer yes. And if the method gives us the answer yes, then the argument is indeed valid. Okay, so that's what we're going to do. We're going to show these two things. We're going to say something about the adequacy of SL, and we're going to show that the tree method is adequate. Okay. In order to prove these things, we're going to need a proof technique. And that proof technique is called mathematical logic. And I would guess that almost everybody in the class, this is something brand new. Okay, so this is a proof technique. It's a way of proving things. And it's a technique that actually gives us a way to prove something about an infinite set of things, about an infinite collection of things. And both of these adequacy proofs, about the adequacy of SL and the adequacy of the tree method, relies on proofs by mathematical induction. Okay, so let me just say as an aside, I will never ask you to prove anything by mathematical induction. But I want you to follow along. I want you to be able to sort of understand in broad strokes what's going on in the two proofs that we're going to be talking about. And so what I want to do first is to talk about what mathematical induction is. One of the things I want to do in this course is to give you a sense of lots of different ways in which things can be proved. So we've talked so far about, we've proved some small, metatheoretical claims. We've shown how to prove something's false by constructing counterexamples. We've talked about direct proofs and indirect proofs. We've seen how to prove conditional claims are true. We've seen how to show that biconditional claims are true. And so mathematical induction is a very interesting technique for proving things. And what's special about it is it gives us a way of proving that every member of an infinite collection of things has some property or other. So it's a proof technique that gives us a way to prove something about each member of an infinite set of things. Okay, so here's a question. How can we prove something about an infinite number of things? How can we prove, so suppose we've got this infinite collection of things, and we want to prove that every single one of them has some particular property. Call it P, property P. Well, we can't examine them all. We can't say, well, that one has it, and that one has it, and that one has it, right? Because there's not enough time. We're going to run out of time, right? Because our lives are not infinite. So we can't just sort of run through and examine them all. So so the way in which we're going to we prove that the members of an infinite collection of things all have the same property is by what's called mathematical induction. Okay, so here's a metaphor that many people find helpful. So probably when you were young, or you played with dominoes. Remember, or maybe I'm sure you've seen. You can do a search on YouTube, and you can see sort of amazing videos of people who have, done these amazing arrays of dominoes. Actually, I just recently saw an ad for a little plastic truck that you can wind up. I'm not sure, maybe it's battery, I don't know. And it's sort of, as the truck, I'm going to draw a truck. As the truck moves, what it does is it drops dominoes that are perfectly spaced. Because remember, if you did play with dominoes when you were a kid and tried to come up with these arrays that would then cascade, right? One of the issues with it was to get your dominoes lined up, so they were just the right distance from one another, so that if you push one down, you'd end up with this cascade of dominoes. And also, like, you didn't want to bump into one, like in the middle, then you'd have to start over again. Or the cat walks by, now this is becoming autobiographical, and knocks them over, and then you have to start all over again, right? So imagine that we have a really, really long line of dominoes that are set up on their ends, okay? So what should be apparent is there's got to be a first domino, right? Because it's got to start somewhere. Okay. And imagine that these dominoes are set up either by that little truck that I just was talking about, or an incredibly patient mother who's helping her kid with this project, reluctantly helping her kid with this project because he wants to play with dominoes. Okay. And imagine that this line of dominoes, well, it might do all kind of curvy things, right? But imagine that this line of dominoes is infinitely long, and it kind of feels that way when you're setting these things up. So imagine that the line of dominoes is infinitely long. It's an infinite collection of dominoes, and they're all lined up on their ends, like just precisely the right distance from one another. But even if it's an infinitely long collection of dominoes, there still has to be a first one, right? Okay, so now imagine that you knock down the first domino, right? So it falls, and it knocks down the second one. And then it falls, and it knocks down the third one. And then it falls and knocks down the fourth one. And so on, and so on. Okay. I imagine that your intuition is that this cascade of dominoes is going to continue forever if we have an infinite collection of them, right? It's just going to keep going and going, you know, forever and ever and ever and ever. Okay. How would you prove this? How would you convince somebody of this? I'm hoping you're thinking about it as I'm writing this down. How would you prove that the cascade is going to continue? Okay, I'm going to give you a minute just to kind of think about it. So we want a rigorous proof, right? I mean, you have a very strong intuition that it's going to continue forever. But how do you actually prove, like, establish that it's true that it's going to go on forever? And here's how you might proceed. You know, and I wish we could have a conversation about this, but here's how you might proceed. You might start off by saying, okay, we can knock down the first domino, right? So, you know, first we knock down domino number 1. And it knocks over domino 2. Okay, that's our first observation, right? So that's what we were talking about up here. And then you might say that in general, a falling domino knocks over its neighbor, knocks over the guy right next to him, right? Because that's where your intuition comes from, right? You get the ball rolling. You know, this guy, you knock him down, and then he knocks down the other guy, and then, in general, you think, well, you know, any domino that falls down is gonna knock down the guy next to him, and so then you conclude, oh, so you know, so all the dominoes are going to fall over. And if you've got an infinite collection of them that are set up just right, that's our assumption, they're set up just right, that cascade's going to continue forever. So this is often offered, this metaphor, and it's a metaphor, right? This metaphor is often offered as kind of an illustration of reasoning by mathematical induction. One of the things about the infinite collection of things that we're going to be dealing with is that it's an ordered infinite collection of things. So one of the ways in which this is kind of a reasonable metaphor is that this is ordered in that you have the first one, the second one, the third one, you know, the nth one, the n plus first one, and so on, right? You can order the dominoes and call them by the first, second, third, fourth, fifth, nth, whatever, 757th, and so on. Okay, and that's the kind of infinite set that we're going to be talking about that can be ordered. So we can talk about the first member of the set, the second member of the set, and so on. Okay, so how can we capitalize on? I hope that you have this intuition, and I'm hoping you're sharing this intuition, and you say, yeah, so this kind of reasoning captures why I think that the cascade is going to go on forever. Okay, and the components of a proof by mathematical induction, this technique that I'm talking about now, always has certain parts. Okay, there's certain components. Every proof by mathematical induction has 2 components and then the conclusion. And the first component of any proof by mathematical induction, it's what's called the base case. And in the base case, we show that that the smallest member of the set, the first member of the set, what I mean by smallest is, so in this case, this is the smallest because it's the first. This is the next smallest because it's the second. The smallest or first member of the set has the property in question. And what's the property in question for the domino metaphor? That when it falls, it knocks down the guy after him. Okay, and we want to show that that's true for every single thing. That when this one falls, he's going to knock down the guy next to him. Okay, so basically, you want to sort of like you want to get the ball rolling, so to speak. So in this case, we showed that when we knock down the first guy, he knocks down the second guy. Okay. So that's the base case. The next part of any proof by mathematical induction is what's called the inductive step. Now, it's called mathematical induction, and the second part of any proof by mathematical induction is called the inductive step. But a proof by mathematical induction is a deductive argument. It's not, we talked initially at the very beginning of the term, it's a deductively valid argument. We talked about the difference between inductive strength and deductive validity. Even though this has the word induction in it, it's actually a deductively valid, or any argument by or proof by mathematical induction is a deductively valid argument. It's not an inductive argument. And I think you'll get a little sense of why it's called mathematical induction as we continue. Okay, so we have the base case. We want to get the dominoes going, right? So the first guy is going to knock down the second guy. Okay. And the inductive step, we want to show that, going back to the dominoes here, just pick some arbitrarily pick some domino, like way out there, right? If we can show that knocking him down is going to make the guy next to him knock down, then, and that's kind of what's going on in this step. So if we can show that, and suppose, let's call this the nth domino. If we can show that if the nth domino has the property, namely that he's going to knock down the guy next to him, then the n plus first domino has, so if this guy has the property, then if we can show that that guy's got to have the property, namely if this guy knocks down his neighbor, then that guy's going to knock down his neighbor, then we will have shown sort of, in general that some arbitrarily chosen falling domino is going to knock down his neighbor. And the way that we express that in general in the inductive step is that if some arbitrarily chosen member of this infinite set has the property in question, then the next member of the set, remember we're talking about ordered sets, right? So we can talk about the first, second, third, fourth. So if you sort of pick some arbitrarily pick some member of the set, the nth or the kth member of the set, if you can show that if the kth member of the set has the property, then the k plus first member of the set has the property, then you've established the inductive step of the argument. So if some arbitrarily chosen member of the set has the property, then the next guy in line, the next member of the set, sorry, my handwriting is getting worse rather than better. Then the next member of the set has the property. Whatever the property is you're trying to show that every member of an infinite set has. And then, so if you've showed the base case, and note that if you show the base case, the first guy's got the property, right? And then you show the inductive step, which is a conditional claim. If some arbitrarily chosen member of the set has the property, then the guy next to him, the next member of the set, has the property, then finally you can conclude that all members of the set have the property. So back to their domino metaphor, right? If we can show, and I think that this does capture sort of your intuition of how you would try to convince somebody that the cascade would go on forever. If you can show that the first guy's got the property, namely he falls down and the guy next to him falls down, so you kind of get it going, and then you arbitrarily choose, way out there or not so wherever, you arbitrarily choose some other domino, and if you can show that he's got the property, then the guy next to him has the property, well, that seems to be sufficient for showing that the cascade is going to continue forever and ever and ever. Okay, so that is every proof by mathematical induction has these parts, these steps. The base case, the inductive step, and then finally the conclusion that all members of the set have the property. All right, and you're probably thinking, huh? And this is this is pretty abstract, and I think what I'm going to do, and I certainly the first time I encountered proofs by mathematical induction, I was kind of flummoxed. But this is good for you. I'm not going to ask you to prove anything by mathematical induction, but I really would like you to have a sense of what's going on and to be able to follow along with the proofs of these two things that I said we're going to be doing during this interlude. Okay, because it's interesting. This is interesting stuff. And also, I want to present this because, it completes the little project that we began. Like, what do we mean by a good argument? Well, we've come up with this rigorous standard of truth, functional truth, and we've come up with this great method for seeing whether arguments meet this standard. But now what we're going to show is the method actually does what we're using it to do. We're going to prove something about the method. So it kind of completes that project before we moved on to the next part of the course. Okay, so what I'm going to do is I'm going to give you an example of a proof by mathematical induction. And this example is actually going to be an algebraic example. And really the only thing you need in order to follow along is sort of high school algebra, which you've done much more recently than I have. So before I do the proof, I'll tell you a little story, which may or may not be true. I think it's it's kind of one of these stories that's gotten passed down. But I'd like to think that it's true. Who knows? There was a German mathematician, scientist, whose name was Johann Carl Friedrich Gauss. His last name was Gauss. And maybe some of you have encountered Gauss somewhere along the line. He lived from 1777 to 1855. And he made really important contributions to a number of fields of mathematics, number theory, differential geometry, and so on. He also did work in astronomy and optics and so on. He was kind of a smart guy. And the story goes that Gauss was a child prodigy. He was a very, very smart little boy, and there are all kinds of anecdotes about how precocious he was when he was even a toddler. And so here's the story that's told about Gauss when he was a little boy. So imagine that Gauss was, little Johann Carl Friedrich was misbehaving in class. And his teacher said to him, Johann Carl Friedrich, go into the corner and add up all the numbers between, from 1 to 100, thinking that would keep him busy and quiet for a while. Go add up the numbers from 1 to 100. And he almost immediately came up with the right answer. So I'm going to give you a moment to see whether you can figure out what the answer is that Gauss came up with. So it's 1 plus 2 plus 3, all the way up to 100. Okay, and Gauss, much to the teacher's kind of dismay probably, thinking that this would keep him quiet, he said, I know what it is. It's 5,050. Well, how in the world did he do that so quickly? And here's presumably what he did. He noted that if he takes the first one and adds it to the last one, he gets 101, right? And then he takes the second number and adds it to the second to the last one. He gets 101. And then he takes the third one and adds it to the third from the last one, and he gets 101, etc., right? Well, there are 50 of those, right? These are just 3. There are 50 of them. So he said, okay, 50 times 101 is 5,050, right? So what he did was he multiplied 100 times 101 and divided it by 2, and he got the answer. So here's a party trick for you, right? If you want to impress your friends, you say, give me any number. I can add up the first, whatever that number of integers is, and give you the answer almost immediately. Okay, so what I'm going to do is I'm going to prove kind of the principle that Gauss was implicitly using when he did this, and I'm going to prove by mathematical induction. So what is it that he was implicitly relying on when he came up with the answer 5,050? And this is what we're going to show, is that the sum of the first n integers, right? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus n, right? Equals, or is, n times n plus 1 over 2. And that's what Gauss was doing, right? This was the n here was 100. So 100 times 101 over 2 is how he got, presumably, or let's imagine that he got the number 5,050. So this is what we're going to show. And we're going to prove this. So we're going to prove this by mathematical induction, because no matter what integer n you choose, this will give you the sum of the first n integers. So this is going to be for all integers n. Okay? All right. And the proof is by mathematical induction. I can't see your faces. I imagine some of you are thinking, why are we doing this? But just bear with me, really. This is interesting stuff. Okay, proof by mathematical induction. So this is going to be, as I said, algebraic, right? So we're going to prove this by mathematical induction. And remember that I said that every proof by mathematical induction, every proof by mathematical induction has two parts. It has the base case and it has the inductive step. And if you can establish the base case and you can establish the inductive step, then you can conclude that all members of the set have whatever property it is that you're trying to show that the members of an infinite set have. And in this case, the infinite set that we are concerned with is the infinite set of integers. And the property that we are going to show that every integer has is that the sum of the first whatever number you pick, integer, is that number times n, that number plus 1 over 2. Okay. So it's going to have two parts. The first is the base case. Now, often the base case of a proof by mathematical induction is really simple, obvious. Sometimes one's mathematics books might say trivial. Often a mathematics book might say, the proofs by mathematical induction, the base case is left to the reader, it's obvious. Yeah, the word obvious, it's like it's a relative term. In fact, there are a lot of jokes about how mathematicians use the word obvious. But in this case, the base case of this proof is pretty easy, as most base cases are. So what do we need to show? The base case is we need to show, remember that the base case is you have to show that the first member of the set has the property. We need to show that this general claim, when I say it, I mean this general claim about all integers, that it is true when n equals 1, because 1 is the first member of the set of positive integers, right? It goes 1, 2, 3, 4. I should say positive integers. Okay, so we need to show that this claim is true when n equals 1. And how are we going to show that? Well, what we need to show is that 1, so if when n is 1, 1 times 1 plus 1, which is 2, over 2. Right? The sum of the first, what is the sum of the first n odd integers, by the way? The sum of the first integer when, sorry, what is the sum of the first n integers when n equals 1? It's going to equal, it's 1, right? There's only one integer, so it's 1. So what we need to show is that 1, when n is 1, times 1 plus 1, which is 2, over 2 equals 1. That's what we need to show. Well, that's not hard to show, right? Because 1 times 2 is 2 over 2 equals 1. Done. Right? So when n equals 1, it's pretty clear that n times n plus 1 over 2 is the sum of the first 1 integers. It's only 1. Okay, so in this case, the base case was not difficult at all. And that's often the case with the base case of a proof by mathematical induction. So what we've done, going back to our metaphor, back to our domino metaphor, we showed, the first guy's got the property. The first guy in this set is the first member of the set of positive integers, 1. So yeah, the sum of the first 1 positive integers is 1. Okay, done. All right, so the next step, which is not as trivial, is the inductive step. Ugh, gosh. And so remember, what the inductive step tells you that what you want to show is that if some arbitrarily chosen member of the set has the property, if some arbitrarily chosen member of the set has the property, then the next one in line has the property. So what we want to show here is that, so we want to show that if it works for some number k, some positive integer k, then it works for k plus 1, right? So if this is true for some arbitrarily chosen number k, that is, if the sum of the first k integers is k times k plus 1 over 2, then it works for k plus 1, works for the guy next to him. Then the sum of the first k plus 1 integers is k plus 1 times k plus 1 plus 1 over 2. And that's what we need to show, and that's where just a little bit of algebra is going to be required. Okay, so in other words, we need to show that this conditional, remember the inductive case of the inductive step of every proof by mathematical induction involves showing a conditional to be true. So we need to show that the following conditional is true. If, do we like green? Sure. If the sum of the first k positive integers equals k times k plus 1 over 2, so if 1 plus 2 plus k, this is the sum of the first k positive integers, equals k times k plus 1 over 2, then the sum of the first k plus 1 positive integers has that property too. So it's 1 plus 2 plus k plus the next guy, k plus 1, right, equals k plus 1 times k plus 1, which is k plus 2 over 2. So this is what we need to show. We need to show that this conditional is true. Okay, so let me just make sure that, let me just back up for a minute. What we want to show, what we're doing here is we're showing that this claim that the sum of the first n positive integers is n times n plus 1 over 2, that it's true for all positive integers. We're proving it by mathematical induction. We've shown the base case. We've shown that it's true for the first member of this infinite set. So that's the base case, right? And now we have to show the inductive step, which is the second part of every proof by mathematical induction, and that's always going to be a conditional claim. If some arbitrarily chosen member of the set has the property, then the next guy in line has the property. Then you can end up concluding that all members of the set have the property. So what we've done so far is we've shown the base case, and now we're going to show the inductive step to be true. And the inductive step, again, is a conditional claim. If it's true for some arbitrarily chosen number k, then it's true for the next guy in line, k plus 1. And this is kind of easy enough. We're going to prove this directly. We're going to prove this in the way we've shown other conditional claims to be true. We assume the antecedent is true. So we're going to suppose the antecedent is true. So suppose that 1 plus 2 plus k, this is in the way. So this is what we're trying to show. 1 plus 2 plus k equals k times k plus 1 over 2. And then we want to show, so we're assuming this, and we want to show that the consequent follows from it, okay? So we need to show one plus 2 plus k plus 1 equals k plus 1 times k plus 2 over 2. Okay, so our inductive assumption, so this, we're assuming the antecedent of this inductive step. Our inductive assumption here says that we can substitute so this is what we're trying to show, right? But we can substitute for this, we can substitute for this, that. We're assuming that this equals that, right? That's our inductive assumption. So, in other words, we just need to show that k times k plus 1, thinking and writing thing, k times k plus 1 over 2, so I'm substituting, since we're assuming that that equals that, I can stick in that for this here. So in other words, we need to show that k times k plus 1 over 2 plus k plus 1, right, this thing here, equals k plus 1 times k plus 2 over 2. Okay, did you follow me? I hope you followed me. Since we're supposing that this identity holds, that the sum of the first k positive integers is this, we can substitute in this that, okay? So now we've reduced what we need to show to that, right? By substitution. And how do we show that? Well, we do this by simple algebra. We just multiply by 2 and divide by 2 this. So we get k, in other words, what we need to show, i.e., k times k plus 1, k, where am I, times k, go away, k plus 1 over 2 plus, and what I'm going to do is I'm going to multiply k, I'm going to put 2 times k plus 1 over 2, right? So this equals that, because what I've done is I've multiplied that and then divided it by 2. Where am I? Equals, well, k plus 1 times k plus 2 is, do you remember this from algebra? K squared plus 3k plus 2, right? That's what, if you multiply that, you get that over 2. Okay? And how are we going to do that? Well, it kind of is obvious, right? Because what we have is, if we carry this out, we have k squared plus k plus 2k plus 2, right? That's what this is. And that's, in other words, k squared plus 3k plus 2 all over 2. Ah! That's exactly what we were hoping it was going to be. So we've just carrying out the simple multiplication, we end up with that. And woo! It worked. We're done. Okay, what was happening there? What we did was we supposed that the claim was true for k, and on the basis of that supposition, we showed that it's true for k plus 1. We just had to do a little bit of algebra in there. Okay, so, all right, this is really different in feeling, nature, and so on from the proofs that we're going to be doing about the tree method, but it's a fairly simple example, albeit it's an algebraic example, of a proof by mathematical induction. It's got the base case, it's got the inductive step. It also has this kind of mysterious quality to it. So, you might be thinking at this point, huh? Really? We've shown it? We've shown that every single positive integer has this property? And when you first, not that you're going to be doing a lot of proofs by mathematical induction. In fact, I promise you won't be asked to do any proofs by mathematical induction. But until you really become extremely comfortable with proving things using this technique, it does have this weird character. And I can remember when I first started learning how to prove things by mathematical induction, I thought, really? Is that all I have to do in order to show that an infinite collection of things has this, all members of an infinite collection of things has this property? And I had either the good fortune or the ill fortune, depending upon how you look at it. When I was learning this when I was in college, I had an older brother who was working on a PhD in mathematics at the time, and I went home for Christmas break, and I told him, so I'm learning how to prove things by mathematical induction. And he kept feeding me, this is like, fun Christmas break at the Russinoff household. He kept feeding me little proofs to do by mathematical induction. And I would say, okay, I would set it up. I understood enough to know how to set up the base case and carry it out, how to set up the inductive step and carry it out. And then I would have this weird feeling, and I'd show it to my brother, and I'd say, well, so what do I do now? And he would look at me and he'd say, write down D-O-N-E. Because it took a long time for me to realize, oh, that's what you need, that's it, I've proved it. Because mathematical induction does have this kind of weird character, initially in any case. Okay, I'm going to stop this lecture here. I hope you enjoyed it. But what we're going to do for the rest of this little interlude is, as promised, we're going to go back in the next lecture. I'm going to talk about the adequacy of the language FL, and then there'll be a handout. This is in chapter 6, but this will be, I'll give you a handout that you can follow along when I do the proof of the adequacy of the tree method. And don't be turned off by this. You'll find what we're doing interesting. And okay, this will not be on a quiz. I will not ask you to prove anything by mathematical induction. So just enjoy learning something new, and don't worry about being tested on it. But also don't think, oh, we're not going to be tested on it because I don't need to learn it, because I do want you to learn it. I want you to understand, as I said, in broad strokes, what's going to go on in the two proofs that we're going to be doing during this metatheoretical interlude. So there might be something that shows up on a quiz having to do with these results. Okay, I'm going to sign off for now. Bye-bye.